You know, everything around us, the phone you're holding, the chair you're sitting on, it all has a secret blueprint. It's this invisible atomic architecture that decides if something bends or if it shatters. Today, we're going to decode that blueprint.
So think about this for a second. We've all done it, right? You can take a metal paper clip and bend it back and forth. But if you try that with a pane of glass, well, you get a very different, much louder result. They're both solid, so what's the deal? What's the fundamental difference here?
Well, the answer isn't really about what they're made of, but how their atoms are put together. And when you zoom way, way down to the atomic level, it all boils down to this epic battle between two forces: perfect, repeating order and complete, jumbled chaos.
And those two choices, order or chaos, they give us the two main ways that nature builds pretty much every single solid you've ever touched.
Okay, so on one side you've got your crystalline structures. I want you to picture a perfectly built brick wall. See how every brick is laid out, super precise, super repeating, three-dimensional. That's what most metals are like, including our paperclip. But then you have the other side, amorphous, total chaos. It's like someone just dumped a pile of bricks on the ground. No pattern, no order. And that's glass.
Now that chaotic, amorphous world is pretty interesting in its own right, but for engineers, the real magic, the real power, comes from understanding that orderly, crystalline world. This is where the blueprint starts to get, well, really, really cool.
So, what's the secret to this orderly world? It's something called the unit cell. And honestly, the best way to think about it is like a single Lego brick, an atomic Lego brick. If you can understand that one tiny piece, you've got the key to the whole structure. It doesn't matter how big it gets, it's all just that same brick repeated over and over.
All right, so let's look at one of the most common blueprints out there. It's called body-centered cubic, or BCC for short. It's actually pretty simple. You've got a cube with an atom on each corner, and then one extra atom just chilling right there in the very center.
Okay, now let's look at another one. It's called face-centered cubic, or FCC. Now we still have those atoms at the 8 corners, right? But this time, instead of one in the middle, we're going to put an atom in the center of every single face of the cube. It might not sound like a big deal, but trust me, this tiny change has absolutely massive consequences.
So why are we getting so into the weeds with these different blueprints? BCC, FCC, who cares, right? Well, it all comes down to one thing: efficiency. How tightly are those atoms packed together? Because as it turns out, that efficiency is what gives a material its strength. And there is actually a way to measure this. It's called the atomic packing factor, or APF. Let's go back to our Lego brick. The APF basically asks, okay, in this box, how much of it is actual Lego, and how much is just empty air? It's the same idea, but with atoms.
So let's look at that first blueprint we talked about, the BCC. Its packing factor, 68%. Think about that for a second. That means almost a full third of the structure is nothing, just empty space between the atoms.
Okay, now remember the FC, the one with atoms on the faces? Its packing factor is 74%. And that jump from 68 to 74 is a huge deal. Why? Because 74% is literally the tightest you can possibly pack spheres together. It's the absolute max.
So here's the takeaway, the thing you really got to remember. That difference between 68% and 74%, it might not sound like much, but in the world of materials, it's everything. Tighter packing almost always means you get a material that's denser, stronger, and just behaves in a completely different way.
Okay, so we've got these different blueprints, but here's where things get really wild. What if a material wasn't stuck with just one? What if it could actually shapeshift? I mean, literally change its atomic blueprint on the fly.
And no, this isn't science fiction. It's a totally real thing called polymorphism. It's this incredible ability some materials have to just completely rearrange their atoms. They can flip from one crystal structure to another, usually just by heating them up or putting them under pressure.
Iron is the perfect example of this. When you get it super hot, we're talking over 912 degrees Celsius, its atoms snap into that super efficient 74% packed FCC structure. But then, as it starts to cool down, right when it crosses that 912 degree mark, bam! The atoms suddenly shift into that less dense 68% packed BCC structure. And think about what that means. It's getting less dense as it cools, so the iron actually expands as it gets colder. How weird is that?
But that weirdness is something we can use. It's actually a secret to making strong steel. When you're making a steel part, the outside surface cools down first, right? So it transforms and gets less dense, but the inside is still hot and tightly packed.
Then, as the inside finally cools and expands, it pushes outwards against that already solid surface. This creates this incredible internal tug-of-war, as the source material puts it. And that locked-in stress is exactly what makes heat-treated steel so unbelievably strong.
So, okay, we can use temperature to control a material's structure. That's pretty cool. But what if we want even more control? What if we want to fine-tune things? Well, that's when we start playing architect, and we engineer things from the inside out by mixing and matching different atoms.
And this is what we call an alloy. It's a super simple concept, really. You just take a metal and you intentionally mix in other elements. We're not just stuck with what nature gave us, with pure iron or pure copper. We're actually designing new materials to be stronger, or to stop them from rusting, or whatever we want. And when you do this mixing, it has pretty predictable results. Those new, different atoms kind of mess up the perfect, orderly crystal structure. And that disruption makes the materials stronger and harder, almost always. A great example is brass. It's just copper and zinc mixed together, but it's way, way harder than pure, soft copper. Now, there is a trade-off. You usually lose some ductility. It's not as stretchy, and it's often not as good at conducting electricity.
And when I say it's not as good a conductor, I mean the effect can be dramatic. Just look at copper. It's an amazing conductor, right? But if you add just the tiniest little bit of another element, a fraction of a percent, its ability to conduct electricity just falls off a cliff. It's just amazing proof that changing that atomic blueprint, even just a tiny bit, can have these huge, massive consequences.
So let's just recap for a second. We started by looking at nature's two basic choices, perfect order or total chaos. Then we figured out how to harness that with things like temperature. And now we're even starting to master it by mixing in new atoms to create alloys. It's an incredible journey. But it leaves you with this one last, kind of mind-blowing question. What happens next? What kind of crazy new materials could we create if we could go beyond just mixing and actually place every single atom exactly where we want it?